And then before we get to the schedulers, and then the quiz 3 has been finished. So yeah, please make sure that you have already taken the quiz 3. And for the grading, I actually run the grading script this morning at 11 a.m., but it takes too long time because I believe some of the students inserted some of the printf messages on their output, and then that actually makes the grading delayed a lot. So it will be finished in an hour or so. So like I create this slide that I updated the score up to lab 3 this morning, but it will be updated after the class. Yeah. And then many students asked me about like how to calculate the total points, about the points to the grade, letter grade. And then I will create new column called the total points. And then you can see the depth points, and then regard that to like see, and then match that to the grading bracket. Then you can easily calculate that. So please ignore what is said from the Canvas about like a percentage, because that's just based on the raw score. And then I will edit my grading script to automatically generate that column and edit. And then we have no final exams. So from now on, the only remaining things are just finishing the labs. And then I'm receiving many inquiries about like the getting more time for the finishing lab 4, and then make an extension for the lab 3, lab 2, or something like that. So what I would like to do is, instead of pushing the deadline to the another like the 1 week or something, because we have no more time than like the December 10th. So I have to push you guys to finish labs earlier, and then that'll be good for you too for like preparing other final exams. And then, but I would like to reduce your burden for the during this pandemic, and then that is getting worse recently. So I would like to accommodate that. So I decided to change the grading bracket from this to this one, and then what this means for you all is that if you connect to this website, there's not a great UI. So I'm not a good UI designer, so yeah, it looks like this. But what you can do is like check all the boxes that you have finished, or you would like to include the score or not. Then it will automatically calculate what will be your expected grade. And then, so what this means is that if you are due perfect on the lab 1, 2, 3, and then finish up to, what is that, exercise 12 or something, then you will get 65. Then your grade will be still A, but maybe you could finish lab 1, 2, 3, and then perfect on the page 1 to 3, but the 0 on lab 4, but you can still secure grade B. So please plan your the time budget, and then please think about that, and then work according to your expectation or something. So, any questions about this? Then I believe, I hope this will be helpful for all you guys. Yeah. And then the most important things are not about the score, things that you guys will learn from this class. So even if you cannot get like the high score on lab 4, it's okay, but please try. And then even if you get 0, you can still secure B. So I would like to have like that kind of safe zone. So please challenge and try. And then for the next, we'll do a little bit of recap about the deadlock theory. And then I decided not to go over like a piece 3 review, because most of the students get 12 over like a 13 kind of thing. So yeah. And then we learned about the deadlock theory, and then that is about like if there is some of the critical section, and then everybody wants to hold the lock, and then not releasing the thing, then there could be some situation that nobody can run forward or something. And then there were 4 cases that we can eliminate deadlocks. And then the case of mutual exclusion is that we need to remove mutual exclusion. That means we should not use lock. And that's irony, But what that actually means is that you do not use lock, just use atomic operation. So that will never create a critical section. So we can replace the locks with the atomic primitives. And then the example of that is we can use compare exchange, which is like a semantically compare and swap for updating the value. So what we are doing is like if we want to add 1 to the previous value, then you have expected previous value, and then only if that value is equal to the stored value, then the value will be updated. So you can still keep all the things consistent without using log and critical section. But actually, we are using log at the processor level at the hardware. So yeah, so you need to know about that. So it's actually removing the mutual exclusion created by software, and then just to align the log at the hardware level. Then you can remove the deadlock situation. And then another case was like the hold and wait. The definition of that is like the one thread may hold one of the lock, and then try to acquire another lock, but it may fail. But if this thread never release lock for this one, then all the thread waiting for the lock of the set A should wait indefinitely. Yeah. And then we can remove this kind of situation by having a meta lock. So whenever we would like to acquire multiple locks at the same time, then it'll be better to have like a one meta lock, and then only if like passing the meta lock, then all the locks can be acquired at the same time. And then all the locks will be released at the same time. If that is like preserved, then you can remove the deadlock situation. And then we also go over like this kind of the thread safe data structure kind of thing. So another way to remove that kind of the hold and wait kind of situation was like we can order the acquiring locks or something. But even if we order that in the code, because we could supply argument in the different order, so that could also cause the deadlock. In that case, we need to have a meta lock like this, then we can remove that kind of condition. And for the null preemption, it's very similar to the hold and wait, but another way to remove that kind of situation for is that, so if one thread acquires the lock and waiting for the lock B, then, excuse me. And then all the thread waiting for A should wait for the this thread acquire B. So that was the problem. So what we can do is like we can implement this on the try lock kind of thing. So what it means is like it tries to acquire two locks at the same time, but the second thing fails, then it will release the first lock and then go back. Then that will remove the problem of the making the thread waiting for the not log of the B, but log of A, but should wait indefinitely. So we can remove that by releasing the log A. And another thing is about the circular wait. So what that means is like thread A1 would like to hold log A, then thread 2 would like to hold log B. That's okay. But after that, thread 1 would like to hold log B, but that is acquired by thread 2. But thread 2 also would like to acquire log A, but that is occupied by thread 1. So that kind of this circular wait situation. So one of the way to remove that was like preserving the order. And then if you really want to use that, then we need to have like a global universal ordering kind of thing. So how can we do that is, so because the pointer in the virtual memory space, so address space is unique to each process. And then if you have two lock variables, then you will have two different addresses for them. And then addresses are unique in a process for the virtual address. Then you can use the ordering by the address. That is one of the trick that you can use for removing the circular wait. So these are the things that we learned about the deadlock. So even if we don't have the deadlock, there could be the case that a process cannot do anything. And then that's about the scheduler. And then I would like to introduce that to you guys. And how you can regard the scheduler is like just an algorithm to choose which process you would like to schedule next. So right now in JAWS, whenever a timer interrupt happens, then we track the execution right from the one environment and then schedule another one. And then in current case, we just go over the EMD's array and then just pick the runnable environment and then just run. And then another case could be if one of the process invokes the sys yield, then that is like the intentionally surrendering the execution right to the kernel. So that would be another case that the scheduler must run. And then to choose which process to run to the next cycle. So right now we are doing the round robin, but there are many algorithms that we can utilize. And then I would like to introduce what kind of the techniques were developed historically. And the important thing here is that the goal of the scheduler is that efficiently running the entire programs on the system. And then it should be fair. What that means is that if one process take up the 99% of the CPU times, but all the other 300 processes should working with the 1% of CPU, then it's unfair. So that is also important. And then there could be some cases that some processes can never be scheduled with some very well-developed algorithm. So we will cover about those kind of cases. And then to introduce why this kind of the thing is very important is that this is a screenshot captured from my laptop. And like it has lots of processes are running. So my ID is blue9055. So it has like few processes based on my ID, but there are lots of system services then running on background. So actually it runs around more than 400 processes at a time, even if I haven't opened some of the web browser or something. So there are many processes. So choosing which to run next is very important for the entire system. And then one thing to note here is that we are with the multi-programming system. What that means is that even if we have a single CPU, we can run multiple programs at the same time. And then we already know that how we can switch the thing back and forth. And then, excuse me. So previously we learned about like the types of the how the operating system can get the execution back from the Ring 3 application. And then that was like if the program intentionally invokes a system call such as sys yield or invokes a system call, then operating system kernel can naturally get the execution from the user level. Then the kernel can freely schedule another one. But the problem was like if one of the program just run while one, then it will never finish, then operating system will never get the execution right back. So I introduced the preemptive multitasking. Yeah. And then those are the background required for the understanding about the scheduler. And then we are mostly focusing on like utilizing the CPU as at maximum. That means like we will make the CPU keep working again and again, and then not making the CPU wasting their cycle. Then that's the goal of the scheduler. So we would like to maximize the system performance out of it. And then one of the example of the why we need the scheduler is that think about there's a job created by Nginx web server. And then that's a web server. It has like there's a connection from the outside, and then the client will send the data. Then the Nginx process will call receive. That's a system call. And then they should wait until the IO operation finishes. So all the packets from the internet should come to our system. Then we can deliver that from the kernel to the user, because the user has no access to the hardware network card directly. So what that means is that, so in the perspective of the Nginx process, when it calls receive, then it should wait until receive returns. So it cannot do anything. So we are actually wasting the CPU cycle. Then what if we can schedule another computation heavy job in between? Then we can like not letting the CPU play like the nothing. So we can keep making the CPU work and again. So we could have a better CPU utilization. So this is an example of like why we need a scheduler for that. So I mentioned about like the when scheduler can take the right and then like choose which process to run. It's like that could be whenever the timer interrupt happens, then the operating system gets the execution right, and then it will schedule again. And then in the non-preemptive style, then like whenever the user process makes a system call or a user process makes a sys yield, then the operating system can intervene and then switch the process. So in non-preemptive systems, so what's important is like there's no method for the preemptively getting the execution back to the kernel. So it relies on the voluntary context switch. So the user program will decide when to switch to the other. But because that has a lot of problem with like the fairness and the others. So right now we are mostly working with the preemptive multitasking systems. And mostly scheduler works whenever like a timer interrupt happens, or whenever there is a very slow I/O operation, such as reading from the disk or reading from the network packet, is involving in the kernel. And then because the previous one, voluntary context switch, so that is the context switch, the interval is determined by the user program. So it is not, it does not have a not reliable responsive time from the system. But in the preemptive systems, so in JAWS, we are actually doing something like that. Whenever there's a timer interrupt and 1 millisecond of time quantum, then we can switch the thing to the another process. So we can make it like the processes keep scheduled. So it'll be more responsive to the users. And then to summarize again about like the goal of the scheduler is that we would like to maximize CPU utilization. Yeah. And then that also could be measured by like how many jobs the CPU required in a certain time, or that could be measured by the responsive time. Yeah. So how quick the program accepts my input and then prints out the result on screen. So both are important depending on the use cases. So for example, if you're doing like the Overwatch kind of the FPS game, then the responsiveness is very important. If you have a lag of like 150 milliseconds or something, then you will die in the game. But another case would be like if you're like playing with some of the downloading some of the stream videos and then like play that, yeah. Then the bandwidth or like throughput of the job would be much more like important. Yeah. So that depending on the kind of the system requirement, we need to choose which scheduler would be the better for it. So please keep that in mind. We will focus on the responsiveness, then throughput of which scheduler can do, and then our grand goal is to maximize the CPU utilization. And then for next, I will introduce each scheduler one by one. So the first thing is very simple. So first in, first out. So it's a non-preemptive scheduler. And then what it does is like schedule jobs based on for their arrival time. So what that means is that suppose a job 1 arrived at this time. So that you can regard this kind of the virtual x-axis as a time, and then there will be job 1. Then, because this is a non-preemptive scheduler, so it will wait until job 1 finishes. But while we are running job 1, there could be job 2 or job 3 could arrive, then you should wait. And then only after job 1 finishes, then we can run job 2 because job 2 comes first. Before then, job 3 arrives. And then after we retire job 2, then we can run job 3. So this is how first in, first out scheduler works. So this is very similar to the somewhat real world scenario. So you can think about this kind of the drive-through and grocery cashier line. So first come, first serve. So this is the thing. So it's quite natural. Yeah. And then let's examine about some of the pros and cons about FIFO scheduler. So process is very fair. So if you want to get scheduled earlier, then come earlier. Yes, it's fair. But the cons are, it could have long average wait time if long jobs or short jobs are mixed. And then let me show you the examples. So suppose we have these 5 jobs, 1, 2, 3, 4, 5. And then job 1 and 2 has a job time as a 10 unit. So you can regard that as a 10 seconds, for example. And then job 3 and 4 and 5, they could be finished in 2 seconds. Then suppose we schedule based on the FIFO, suppose all the jobs arrived at because in sequence 1, 2, 3, 4, 5. Then we run job 1 first, 2, 3, 4, 5. Then we can measure the average wait time. What that means is that the job 1 never waits, so it waited 0 seconds. Then after waiting 10 seconds, job 2 can start. So job 2 waits about 10 seconds. Job 3 waited for 20 and 2 seconds and 24 seconds. So like you can easily calculate how long each job should wait for. And then average wait time is like we add up all these kind of the seconds and then divided by 5. So you can get like the 15.2 seconds of the average wait time. Then let's schedule it differently. Something like this. And then let's measure average wait time of each job again. Job 3 waits 0 to 6 seconds, 4 seconds, 6 and 16 seconds. So you can see that there are significantly lower wait time. Yeah. So the average wait time is 5.6 seconds for this case. Yeah. So the optimizing the average wait time is not always good for for the general systems. So, but there could be this specific system. This scheduler could be beneficial. Yeah. And then because there is like this kind of this significant difference on the number of jobs that you can retire, and also reducing the amount of time for the average wait time. So after seeing this, you might think about, oh, it could be better for scheduling shortest job first, then we could get lower average wait time. So the next scheduler is called SJF, shortest job first. So it's also simple thing. And then it is also called as the shortest remaining job first, but conceptually is the same. And then what that means is schedule the process that has a early finish time first. That's it. But I mentioned that this is not the grand solution for every system. The reason is, the problem is that it'll be very hard to know about when the job will be finished. So think about it. If you have a static data in the program, then you can easily guess like when it will be finished. But if you are dealing with something user, or if there's a lots of delays from the outside, for example, receiving internet packets or something like that, then you might don't know when the program should finish. Yeah. So systems are actually designed for, each of the process announce their expected finish time first. And then if they finish it earlier, that's good. If they require more time, they will extend the time. Then think about some of the Melissa's case. Yeah. So if I want to schedule first every time, then what I can do is set my job finish time as 1. And then right before my execution finishes, then I request operating system that I need one more time slot. And my job time will be 1 again. And so my job will be scheduled again and again and again. So that is the drawback of the shortest job first pair grouping. So this is called a starvation. And then because scheduler will never feed to the sum of the processes, because if I just keep like my finishing time is 1, 1, 1, 1, 1. Yeah. So the problem is that, so let's take an example. So suppose we have a job that requires 10 seconds to finish. And then before it will be scheduling, suppose here a 1 second job comes in. Then the scheduler is implemented if they are implemented as SJF. And what it will do is scheduling it like this. Shortest one first, and then job 1 later. Then job 1 still waiting. And then luckily, the job 1 sees the moment that right next to the schedule. This one will be scheduled, and then next is my turn. Yeah. So the job 1 is expecting that. But there could be the case that another 100 process comes in with the shortest job, then job 1 will be sent back from the scheduler. So to figure out some of the real world examples, I believe it's similar to like some of the fast pass in the amusement park. So even if you waited for 3 or 4 years, if the chunk of the customers with the fast pass comes in, and your wait time will be longer. Yeah. So there's a drawback. Then how can you make it fair? So the easiest way to make it as a fairness scheduler is like running it as a round robin. So that's why the current JAWS is implemented in that way. So that actually guides you to implement a round robin scheduler. Yeah. And then what it does is like this preemptive multitasking. And then similar to what JAWS is doing. So each test will get a fixed time content. So that could be 1 millisecond, 10 milliseconds, depending on the system. And then if the task is not completed, we stop the operating system, stop the user process, and then get the execution back to the kernel and then switch to the other process. And then that process will be still remaining as a EMV runnable, something like that. Then the scheduler knows that the next time they can schedule that process again. And then like there's another factor that about picking the time quantum. So if you set the time quantum as a 1 millisecond, what that means is that the context switch is happening every 1 millisecond. And then now you guys know that what's happening, what the kernel is doing when the context switch happens. So context switch, to have a context switch, the user either invoke the system call or interrupt. And then from lab 3, we learned that for the interrupt handling, we need to store all the register values, all the trap frames, and then we run several lines of the kernel code, and then run over the list of the environments, then pick the next one and get back. So the context switch is not free. It requires some of the CPU time, and then user and kernel switch is also slow. So that consumes around 1,000 cycles or something. So what that means is like just switching from the user to kernel, that requires like consuming the time for the running 1,000 instructions. Yeah. So it's not free. So what that means is that if you do context switch too frequently, then you will spend a lot of time just for context switching, and then not about actually running the job. So for designing a system, it's very important to measure that kind of time, and then choose the right time for the general systems. So the 1 millisecond or that kind of timer interrupt is not determined arbitrarily. So it's more empirically, so that they evaluated the less of the workload, and then Linux or Windows that they determine the different timer interrupt. So yeah, under the hood, there's some of the engineering like that. And then to show you about the round robin examples. So round robin, we do not care about this kind of the job finish time because we will run the job as like a one-time slice and then one-time slice again. Then those kind of the time limit 2 will be retired with the second round. Then third round, fourth round, fifth round, and then we can keep running 1 and 2. Then it's actually fair because it will give one-time slot for each, then again and again. Yeah. So the process of this approach is like it's fair, and then there will be no starvation. So if you just wait, then it will give like a one-time slot for each process, and then again and again. But the problem is like there could be too many concepts switch. So just see it. So this is a summarized figure. And then we are all running the same jobs, but just count the number of the context switch happens. 1, 2, 3, 4. 1, 2, 3, 4. But there are lots of context switching here. So that's the important point about the round robin schedule. So to summarize the pros and cons of each one. So FIFO is also fair. So please come first if you want to be served first. Yeah. But the cons of this approach is like it could have a high average wait time, and then that means not that responsive. And then to make it more responsive, we can easily think of like the shortest job first kind of algorithm. So good thing about this is like it has lower average time, wait time, but the problem is like it could have a starvation problem. So if shorter job comes again and again, then longer job will never be scheduled. And then next thing is about the round robin. And then because it relies on the timer kind of thing, so they could be fairly scheduling all the jobs and then again and again. But the problem is that there could be too much context switch. And also it will have high average wait time than SJF because these two time limit jobs should also wait for the longer time like this. And then these are some of the basic schedulers. And then from the shortest job first, you guys can think about like we use the job, the finish time as a priority for the scheduling. Then that means we can use another factor as a priority for that. So naturally, we can think about the priority scheduling. So that you can regard the priority scheduling as a generalized version of the shortest job first. So what this means is that, so for a scheduler, we will define the priority of each job. So that it could be based on the time limit, finish time, or it could be based on the user definition. Yeah. So for example, some of the important jobs. So suppose you're driving the Tesla autopilot, then the most important thing is like sensing the what are there on the road or kind of thing. If there is any kind of delay, then it could be very dangerous. So we need to be very responsive for that kind of process. Then we could give the highest priority for those kind of things. So we can let them scheduled again and again. Then in contrast, there could be some of the non-important, non-critical jobs. For example, playing the music. So it's important to some of the people, but the things are, okay, if there's a lag, and it's just, damn it, that's it. Nobody dies. But for this case, there's something dangerous could happen. So that's the how we can use like the priority scheduling, for example. And then, so now you can see like the two numbers in each job. And then what this means is that the first number is the job length. And then second number is the priority. So in the case of the SJF, we use the job length as a priority, but right now we could have like a separate priority on the process, and then that is defined by the user or operating system, or a system setup. And then based on that, we can schedule that. So in this case, suppose if the priority 1 is the highest, then the bigger number means the lower priority or something. Then the one with the priority 1 will be scheduled first. 2 will be scheduled next, 3 and 4 and 5, something like this. So it's not like a random kind of thing. So it's based on the user configuration kind of fashion. But you can easily see that this shares the starvation problem. So the same thing could happen. For example, shortest job first. Starvation case was if the shorter job comes again and again, longer job will never be scheduled. So the same thing may happen. Starvation in priority scheduling step. Suppose there's a process with the priority 1, priority 4, and it'll be scheduled like this. And then if the priority 1 jobs comes again and again, then it will suffer this similar kind of starvation. So how can we remove this kind of starvation? So one of the easy way to do that is like we can reward some processes that have been waiting for a while. So for example, this longer job time 10, comes with the priority 4. But if this process have waited for 1 time slot or 1 scheduling or something, then we can reduce and we can increase the priority. So from 4 to 3, 3 to 2, 2 to 1, then eventually it'll be scheduled. So that is called aging and priority scheduling. So what we can do is like based on the wait time of the process, we can increase the priority for the process who waited for a long time. So it's something like try to solve some of the starvation problem with the collaborativity, something like that. Yeah. And then we can also decrease the priority if the one of the process have been already scheduled. Yeah. So that we can do the aging in 2 ways. So we can do the both, or we can do only one side. And that kind of decision is depending on the characteristics of the jobs that your system will have. So let me go over the example of the aging and priority scheduling. So previously, if the shorter job comes again and again, then priority scheduling can also get us started. But how we can do this is that, so suppose we have these 3 jobs. Gray and green jobs are with the priority 1, high speed. And then blue job is like the 10 seconds, requires 10 seconds to finish, that it has a priority 4, and is the lowest priority. And then to schedule it as a priority with a priority scheduling, we could choose either one of these process to schedule first, because both has the priority 1. And what we can do is, like, suppose we schedule the gray one, something like this. Then after running the gray one, we will decrease its priority to 2, because that process has already consumed 1 of the time slot. So we also decrease 1 time unit, then decrease privilege by 1. And then another thing we need to do for the processes that has been waiting in the waiting queue. So we will not decrease the running time because we did not run these jobs, but we are increasing the priority 4 to 3, but 1 is the highest one, we cannot change it, so 1 to 1. So something like this. Yeah. And then suppose the second green one got scheduled next. Then this one was waiting, so it will not decrease the running time, but it will increase the priority. And then the process that is executing right now, it will be decreased for its time execution time, but it will decrease. It will also decrease the priority. And then waiting at the process waiting in the waiting queue also increases the priority by 2. So then for the next, we can schedule this one, because this one has a priority 1. So this one will become priority 2. Then finally, our longest job, then lowest priority. That's the highest priority. And at the end, it could be scheduled like this. So I tried to, I made this kind of animation, but I know that the animation is a little bit complex, but if you just follow the color of the process and then things is step by step, then you can easily get the things about like after the execution time decreases, and then also priority decreases, and then after wait, priority increases, something like that. So changing up the priority value will give us a better opportunity for scheduling. So the lower priority job can be scheduled for like a waiting for a certain amount of time. So we will never have like the starvation, but it could have like a longer responsive time for the longer job. But we could have like the hitting the sweet spot in between, either of like the starvation or like the completely fair kind of thing. So most of the operating systems for now is relying on the priority scheduling because there are some of the critical jobs that we should do, should run very responsibly. And then on the Linux systems, it is defined as a so-called nice value. I don't know why it's called nice, but you can go to this website to read about some of the history of that. And then in Linux, how it uses like the nice value minus 20 is the highest priority. And the nice value of 19, maybe 19 or 20, that is the lowest priority. And then default value is 0. So if you run the program, mostly it's running with the nice value 0. But if you want to make your process more responsive, then you can set it as minus 20. And then another thing in the Windows is that so it has like the priority, something like so if you open the test manager, right click on the process, and you can set the priority. So it has a normal, above normal, high, real time. So it's based on some of the similar to this kind of the nice value. Now, internally, it has some of the integer value for each of the priorities. So you can regard the implementation would be somewhat very similar. And then because the priority scheduling is a generalized version for the like any kind of the thing that you can prioritize the process. So we can regard SJF as the priority based on the job length. And then FIFO as the priority based on the job arrival time. And this is the end of the lecture for today. And then feel free to ask any questions about the scheduler. So although we didn't go over the implementing of this kind of the scheduler in JAWS, so this part is very important. And then, so from the diagrams and the examples, you can easily expect that there could be the cases that some process can never be scheduled, or it is not responsive, and that could be problematic. So the engineering for the scheduler is very important. Any questions? Yes. Could you repeat the question again? So for this kind of case, the nice, and also for the Windows case, the program itself can change it. But depending on the operating system, you can design it as like the operating system can change it, or like only the system administrator can change it, so they can configure it like that. But right now, you can freely change the values like that. So for this kind of the right click and then change the priority, that does not require administrative privilege in Windows. And then program itself can also invoke a system call to change their nice value. So that's the current implementation, but we can implement the operating system to never have like a system call for the changing the priority. Then we can design the system as the operating system or administrator sets the priority. Does that answer your question? Thank you. All right, if there's no more questions, then let's conclude the lectures here. And then the lecture on Thursday will be the final lecture. So what I will do is like I will choose a little bit of like how modern operating system are designed, and then I will also go over like the summary of like what you guys have learned. And then I will have like this a little bit of like some kind of questions and answers that you may utilize for those of the some of the job interview questions. So that will be fun. So please don't miss the last lecture. All right, thank you, and then thank you for working hard for the lab 4. I know it's painful working with the 4 CPUs. It's totally different debugging. Yeah, but make sure to use lots of printf, PDB. Yeah, and then if you cannot understand why it is happening, then from the printf, try to draw like which environment schedule first, and then what it does. Then you can figure out like, how it stops at a certain point indefinitely or something. And then whenever there's a page fault or like some of the panic, then the easy thing that you can do is just print the frame. And from the say the EIP, you can locate where it is. And also from the CR2 register, you can read about which address generate the fault. Yeah. And then mostly you will deal with the null pointer reference most of the cases. And if you find where it is, then you can easily fix that and move forward. I've seen the several students like stuck at the 4 hours for the very simple bug in the code or something. But the problem is that if I know how you guys code, then I can summarize the potential bugs you will meet. But the beauty of this class, maybe a headache of this class, is that all the JOS is implemented by you. So all the code is different. So the bugs you are encountering is different from one to each other. So that's the difficult part, and that's why we have plenty of the TA on the server. So please utilize the TA, but please do not utilize much for the human developer. Right. Thank you, and then feel free to come down to ask more questions.
Yes, sir.